These are your notes for Unit 4, Day 2 of Calculus. If you would like to see the completed warm-up, the review question, or any homework questions we covered in class today, just look at the finished notes. So today we're going to continue talking about integration and integrals. We'll talk about Riemann sums, so finding the area between the curve and the x-axis using shapes like rectangles or trapezoids. We'll continue talking about using the sigma terminology, so the big capital E, and how we use that to define definite integrals. And we're going to talk about some properties of definite integrals. And I'll show you how to use Desmos or your graphing calculator to evaluate a definite integral. So last class we talked about Riemann sums and we talked about sigma notation. But again, an integral, when you're finding an integral, and for notation we can use that elongated s, and then it's f of x, which is the height of each of your rectangles, times d of x, which is the width of each of your rectangles, and then you're summing all of those. You are finding the area between the curve and the x-axis. So again, the whole purpose of integration is to find the area between the curve and the x-axis. So on this little piece down here, when we're finding the area between the curve and the x-axis, since it's below the x-axis, that integral, when we evaluate it, is going to be negative, because it's below the x-axis. Now again, that doesn't represent a negative area in the sense that you're thinking. It just means that the amount that's accruing, or the amount, like if you're thinking about this as a displacement, if this is a velocity curve and you're finding the area, is moving in the negative direction. Or if the rate of change is like you are shoveling snow, it's the amount of snow that you removed during that time. And then if we're doing it on the other side where the curve is above the x-axis, when you do the area under the curve, this area, so this integral, is going to be positive. So that means that the amount that's accruing is positive. So if this is snow that's falling, then the snow is accumulating on the ground. And on the other side of the curve, it could be like melting snow, if you wanted to think about it like this. So this would be snow that's melting, and this could be snow that's falling and accumulating. With sigma notation, so remember sigma means sum, so you're summing, and then this piece right here, the f of x times delta x, is the height times the base of each of those rectangles. And so you're summing the areas of the rectangles. And so that's sigma notation. And so in a second, we're going to talk about how the sigma notation and the integration notation, how we can move between the two different forms of integration. Something to keep in mind, that if a function is continuous, so if f of x is continuous on some sort of interval, so on some interval from a to b, then the integral from a to b, the area under the curve from a to b, exists. So you can find the area underneath the curve as long as the function's continuous. So as long as there's no holes, jumps, or asymptotes between a and b on the graph, you can definitely find the area. If there are holes, jumps, or asymptotes, that doesn't necessarily mean you can't find the area. And in a lot of cases, you still can. But all this is saying that if a function is continuous between 2 points, then you can find the area of that function between the 2 points, or the area between the curve of that function and the x-axis. So, like I said before, we'll talk about how the integration notation and the sigma notation are used and are interchangeable. So this is the integration method. And so this is just saying if you find the area under the curve, or I guess not necessarily under the curve, so it's the area between the curve, so between the curve f of x and the x-axis, between x equals a and x equals b. So that's what you're doing. And then f of x would be the height of each of those rectangles, and d of x is the width of each of the rectangles. And basically what this means is that if you integrate from A to B, there's going to be an infinite number of rectangles. Oops. So that elongated S is the integration symbol, and it's an S for sum. And so the pieces that are the same, so the two pieces that are same between integration notation and summation notation, so this is the summation notation, because that big E is the sum. So if we want to integrate between A and B, that is this piece right here. So that means we're going to have an infinite number of rectangles, and that's what this means. We're going to have an infinite number of rectangles. And then the other two pieces that match up, the f of x is the height of my rectangles, and that is f of each different x value. That's what that represents in the summation notation. And then you have d of x, and d of x is just a way of writing delta x. And same thing here. That's actually the delta symbol. So those are the pieces that match up between the integration notation and the summation notation. So going even more specifically, in your integration notation, this top letter B is called the upper limit of integration. So it's like where you're ending on the x-axis. And that bottom A is called the lower limit of integration. So that's where you're starting on the x-axis. So that's the start x value. And this is the end x value. And then the elongated S is called the integral sign. And then the f of x, the actual function that you're integrating, is called the integrand. And then the dx is going to be the variable of integration. So we'll see problems where it's not d of x, it's like d of y or d of a. It's telling you what variable you're going to integrate, or which variable you're going to undo the derivative of. And then how we read this is we read this as the integral of f from a to b, or you can read it as the integral from a to b of f. So when you find the value of the integral, you have evaluated the integral. So that is a definite integral because you're evaluating from a specific x value to another specific x value. So that is a definite integral. All right, so let's go from summation notation back to integral notation. So I told you that this piece right here is the same as the integral. So we're going to integrate, and we're going to do an infinite number of rectangles, and it's telling us to start at 0 and end at 2. So we're going to integrate from 0 to 2. And then notice here, it's saying ck squared. So that's like your f of x. So we're saying that it is x squared. So our thing that we're evaluating is x squared. And then the delta x is your dx. So this is telling you to integrate from 0 to 2 x squared dx. All right, so using that same idea, see if you can pause the video and do the problem below. See if you can take that summation and write it as a definite integral. All right, so we're going to integrate from -7 to 5. So we're summing all of the rectangles, so an infinite number of rectangles from -7 to 5. So start at -7 and end at 5. And here is our function. So it's saying x squared minus 3x. And then we have our delta x, so that's our dx. There you go. That's changing from summation notation to integration notation. All right, and so we talked about this. So the bounded area, so if you're going to start at a specific value of x and end at a specific value of x, that is called a definite integral. The areas above the curve you view as positive, and the areas below the curve we're going to view as negative, even though areas aren't negative. So what you're going to do is you're going to take all the areas above the curve and then subtract all the areas below the curve, and that's going to equal your total displacement. If we're talking about if this was a velocity graph, then that would be your total displacement. So above the curve, that would be when your particle is moving to the right, and below the curve is when the particle is moving to the left. And so if you add all of those up, and then view the ones underneath as negative, that would be your total displacement. That's how much you would be away from your starting position at the end of that movement. All right, so let's look at these. Sketch the region whose area is represented by the definite integral and evaluate the integral using an appropriate formula from geometry. All right, so I'm going to put in a graph for these. Let's shrink this down. So let's graph each one of these. All right, so let's start with that first one. So we are integrating 2 from 1 to 4. So 2, if I graph that, y equals 2 is just a horizontal line. So we're going to go a horizontal line, 2 up. And so that would be f of x. And I want to start at 1, and I want to end at 4. So I'm just going to find the area underneath the curve, so between the curve and the x-axis, between 1 and 4. So I'm finding the area of that box. Well, to find the area of that box, it's just going to be base times height. The base is 3, the height is 2, and so this is just going to be 3 times 2. So that definite integral is going to be 6 because the area under the curve, so between the curve and the x-axis, is 6. On B, we are going to do x plus 2. So we're going to start 2 up, and then we're going to go up 1 over 1, up 1 over 1, up 1 over 1, down 1 over 1. And so that's going to be f of x. It's going to be x plus 2. And then they want us to start at -1 and end at positive 2. So I'm finding the area between the curve and the x-axis, so it ends up being that shape right there. And that's a trapezoid. You could also change that into a rectangle and a triangle above it, but we'll do the trapezoid. And so remember to find the area of a trapezoid. It's base 1 plus base 2 times the height divided by 2. So my two bases are going to be, here's my first base, so my first base is 1. My second base is 1, 2, 3, 4. And then on the side would be the height. So the height of my trapezoid is 1. So this definite integral is going to be base 1 plus base 2, so 1 plus 4, times the height, which is 3, and then divide by 2. So this is going to be 5 times 3 divided by 2, so it's going to be 7.5. So the area under the curve between -1 and 2 of x plus 2 is going to be 7.5. All right, the next one, if you remember from last class, when you have the square root of r squared minus x squared, this ends up being a semicircle. And since it's the positive, it's going to be the upper semicircle. If it was negative, it'd be the lower semicircle. So this is a semicircle. The radius squared is 1, so the radius is going to be 1. So I'm going to blow this up. So I have a semicircle of radius 1, so it's going to be this guy right here. And so we're trying to find the area between 0 and 1. So I'm just trying to find this area right here, which ends up being a fourth of the circle. So that's 1/4 of the area of the circle. And the radius of this circle is 1. So it's going to be 1/4 times pi times 1 squared, which is just going to be 1/4 pi. So the area between 0 and 1 of the square root of 1 minus x squared dx is going to be 1/4 pi. And that's how we can use some common geometric areas to find definite integrals. So if you can graph the function, then you can find its definite integral just by finding the area between the curve and the x-axis. All right, why don't you pause the video and try this one. Find the area between -2 and +2 of the square root of 4 minus x squared. All right, so I'm going to paste another graph here. And so this is going to be another semicircle. This time the radius is 2, and it's the upper half of the semicircle because it's positive square root. And then we're going to go between -2 and +2. So I'm finding the whole area of that semicircle. And so the area of a semicircle is pi r squared over 2. And so the radius is going to be 2, so it's going to be pi times 4, which is 2 squared, and then all over 2, so this is going to be 2 pi. So the area, or the definite integral from -2 to +2 of the square root of 4 minus x squared is going to be 2 pi. So some properties of definite integrals. So the first property says that if you integrate from a to a f of x d of x, you should get 0. Why does that make sense? So if you have a picture and you're trying to find the area and you're going to start at A and end at A, what's the area under the curve? Well, you didn't move anywhere. It's like if you're trying to find your displacement and you started at time 0 and ended at time 0, you haven't moved anywhere. So if the starting value and the ending value that you're trying to integrate from are the same, then that definite integral is going to be 0. If you are integrating, and we're going to start at A and end at B, and we want to find the area under that curve, then you would get the integral from A to B of f of x times d of x, right? Well, what happens if I switched those bounds? What if I made it from B to A of f of x dx? So instead of integrating this way, we're integrating this way. The only thing that happens is it's going to be the exact same area, but since we're moving in the negative direction, it's making that area negative. So it's going to be the opposite of the integral from A to B of f of x dx. So if your bounds are in the wrong order, you can put them in the right order by pulling out a negative sign. All right, so let's look at another one. Let's say we are integrating from A to B, but then we have some value C in between. Well, the entire area would be the integral from A to B of f of x dx, right? That would be the area of the whole thing. But if we wanted to, we could split it up into two separate areas. We could take the integral from A to C, and that would be that first piece. And then we could take the integral from C to B, which would be that second piece. And if we added them together, you would get the whole area from A to B. So you can separate integrals into separate integrals if you want to by breaking them up with a point in the middle. So some other properties are down below. If an integral has a constant in front, you can pull that constant to the outside if you want to. So for instance, if I had the integral from A to B of 3x dx, if you want to, you can take that 3 and pull it to the front because it's a coefficient. So we could have 3 times the definite integral from A to B of x dx. You don't have to, but you can. If you are adding on the inside of a definite integral, so f of x plus g of x, you can separate it into two separate definite integrals if you want to. So the integral from A to B of f of x plus the integral of A to B of g of x. So for instance, if you had the integral from A to B of x squared plus 3x, if you want to, you could separate this into two separate integrals. You can take the integral from A to B of x squared dx plus the integral of A to B of 3x dx. Again, you don't have to, but just know that you can separate them. The same thing works with subtraction. So if you have two different functions and you're subtracting them in a definite integral, you can separate it into two separate definite integrals with subtracting them in between. And so those are properties of definite integrals that you can use sometimes, and they'll make your life a little bit easier. So let's see how these would work in some examples. So up top, they're giving you some information. They're saying if you integrate from -1 to +1 of f of x, you get 5. So for instance, if we started at -1 and we ended at +1, and we've just got a picture, right? So that area right there would be 5. That's what it's saying. And then if you integrate from 1 to 4, if you integrate from 1 to 4, so starting at 1 and ending at 4, you have an area of -2, which means that it would be below. So that area could be -2. And then we have a totally different function. We have h of x. So if I take h of x and I integrate from -1 to +1, I get 7. So we'll take another area. And so that area would be +7. All right. So A says, what if I wanted to integrate from 4 to 1? Sorry, my dog is playing with a toy. What if I wanted to integrate from 4 to 1? Well, notice what's wrong with that. The bounds are in the wrong order. So the property said that I could put the bounds in the correct order by pulling out a negative sign. So it's the same thing as the opposite of the integral from 1 to 4 of f of x d of x. And up here they told us if you integrate from 1 to 4, you get -2. So it's going to be the opposite of -2. So it'll be +2. All right, let's look at B. B says, what happens if we integrate from -1 to +4? Well, I have -1 to +1, and I have 1 to 4. So remember, if I have two separate ones, I can add them together to find the full integral. So the integral from -1 to 4, f of x, is the same thing if I took the integral from -1 to +1, f of x dx, plus the integral from 1 to 4 of f of x dx. And I know both of those. From -1 to +1, I get 5. And from 1 to 4, I get -2. So the total area would be 3 between -1 and 4. All right, let's look at C. C says, what if I want to integrate -1 to +1 of 2 times f of x plus 3 times h of x? Well, I know -1 to +1 of f of x. So if I want to integrate -1 to +1 of 2 f of x plus 3 h of x dx, I can separate this into two separate integrals. So it'll be -1 to +1. I can pull the 2 out in front, f of x d of x. Then plus, I can pull the 3 out in front, -1 to 1 h of x dx. So those are just using the properties of integrals that we learned up above. So this will be 2 times 5 plus 3 times 7. So this will be 10 plus 21. So this would be 31. All right, what if I want to integrate from 0 to 1 of f of x? Well, I don't know how to get an exact answer, but I can write this as an expression. So I'll write it up here. I know that if I wanted to find 0 to 1 of f of x, well, that's what I'm trying to end up with. All I know is what happens if I go from -1 to +1. Well, if I broke up -1 to +1, what if I broke it up to -1 to 0 f of x dx plus 0 to 1 f of x dx? I would get the entire integral from -1 to 1 f of x dx, correct? So what I'm trying to find is this guy. I'm trying to find 0 to 1. And the only piece of this that I know is from -1 to +1. I know if I go from -1 to +1, I get 5. So now I have -1 to 0 f of x dx plus what I'm trying to find, 0 to 1 f of x dx, I get 5. So if I want to solve for this, I have to get rid of the -1 to 0. So I would just subtract it to move it to the other side. So I have 0 to 1 f of x dx is going to equal 5 minus -1 to 0 f of x dx. And I don't know what that is, but that would be the expression that I would use to find D. All right. E, I want to go from -2 to +2 of h of x. This one, I only know the middle one, from -1 to +1 is 7. So if I wanted to write it as a big expression, I would have to write it like this. So E, we're trying to find -2 to +2 h of x dx. Well, I know that if I integrate from -2 to -1 h of x dx, plus then I integrate from -1 to +1 h of x dx, and then I integrate from +1 to +2 h of x dx, I would get the entire thing. Well, the only piece of that I know is that middle piece, and from -1 to +1 is 7. So other than that, -2 to +2 h of x dx, the integral of that would just be that expression with a 7 in between. For f, again, I know what -1 to 4 of f of x is. We found that earlier. That was b, so this part would become 3. So it'll be 3 plus the integral from -1 to 4 h of x dx. And again, I don't have enough information to write that, so I'm just going to leave f like that. And so that's using the properties of definite integrals to try and rewrite some expressions. All right, so let's evaluate the integral from 0 to 1 of 5 minus 3 times the square root of 1 minus x squared. I'm going to break this up. I'm going to write this as the integral from 0 to 1 of 5 dx, then minus 3 times the definite integral from 0 to 1 of the square root of 1 minus x squared dx. And now what I'm going to do is I am going to draw the graph of both of these. And then I'm going to find each of those areas and do it one at a time. So on this first one, we have the integral of 5. So 5 is just a horizontal line, 5 tall, 1, 2, 3, 4, 5. So that would be the graph of the first one. And then I want to go from 0 to 1. So I want to start at 0 and end at 1. So I am just trying to find the area of that rectangle. Well, the area of that rectangle, the base is 1 and the height is 5. So the area of that rectangle is just 5. And then I'm going to subtract 3 times, well, this one is going to be a semicircle. We graphed that earlier. So the radius is 1 and the height is 1. And so it's that guy. And we want to go from 0 to 1. So I just want that quarter of the semicircle. So it's going to be 3 times pi. The radius is 1 squared. And since it's a quarter of the semicircle, it'll be over 4. So this is minus 3 pi over 4. And so that definite integral would be 5 minus 3 pi over 4. So we can break up that definite integral into pieces using the properties, and then we can graph the parts that we want and then find the areas on the graphs. All right, so definite integrals on a calculator. I'm going to show you how to do this on Desmos, and then I'm going to show you how to do it on a TI-84 if you have one. And then the Casio, you might, if you have a Casio, then you'll bring it to class and I'll show you how to do it on a class, during class. So on Desmos, what we can do if you want to find a definite integral, you're going to do functions and then do miscellaneous. So the MISC, and then it's on the bottom left side, it's the little integral sign. And then you literally can type in what you want. So if we want to find, so you do functions, and then do the miscellaneous, and then it's all the way down at the bottom, and it's the little integral sign. And let's say we want to integrate from 1 to 3. Well, actually, let's just do the one we just did. So let's say we want to integrate from 0 to 1, and then it was 5 minus 3 times the square root of 1 minus x squared, and then dx. And then we got 5 minus 3 pi over 4, correct? So let's see if that was the right answer if we did it on Desmos. So we are going to integrate from 0 to 1. And then we're going to do parentheses. And then it'll be 5 minus 3, and then the square root of 1 minus x squared. Oops. And then you're going to have to do dx. So make sure you put the dx in at the end, or Desmos will say you don't have the right information. So you've got to type this in exactly like it looks into Desmos. And so this is saying that the answer is 2.6438. And so if I did 5 minus 3 pi divided by 4, notice that that's the exact same thing, 2.6438. So you can find that definite integral by graphing it, or you can also use Desmos or a graphing calculator. So that's how it works on Desmos. On a TI-84 or on a TI, you're going to hit the math button, and then you hit 9 for the definite integral, and then you get this, and then you get these little boxes. So you're going to do 0 and 1, and then you'll type in the function, and then you're going to type in an x right there, the xt theta button, xt theta n. You do that for n, and then you can hit enter, and then it'll give you your definite integral. On a Casio, I think you hit option calc. I believe that's the keystroke. And then it gives you that, and then you're going to type in the function. And then you do comma 0, comma 1. So on a Casio, that's what you would do. So it doesn't let you type in those little 0 and 1s where they would go. So you hit, after you're done typing in the function, you hit comma 0, comma 1. All right. So let's go ahead and use Desmos, or you can use your graphing calculators to try the following ones. So we are going to integrate. So function, miscellaneous, the integral sign. We're going to integrate from 1 to 3, and then parentheses, 2x squared minus 12x plus 13, and then comma, and then we're going to do dx. And there we go. So this definite integral is negative 4.667, or negative 4 2/3. On the next one, function miscellaneous, and then when we are going to integrate from 0 to 3, and then parentheses, negative x cubed plus 3x squared minus 2, and the parentheses, and then dx, and then we get 0.75. All right, let's look at the next ones. Well, actually, when you're doing trig functions, just make sure that your calculator is in radians. So make sure you hit mode and make sure your calculator is in radians. In calculus, we're always going to use radians. So let's try the next one. So function integration, negative 4 to negative 1. And then we'll do 4 divided by, oops, this is negative, divided by x cubed, and then dx, and we get 1.875. And then on the next one, we're going to integrate from negative pi divided by 4 to negative pi over 6, and then we are integrating 2 and then cosine x, and then dx. And then for Desmos, to make sure you're in the right form, hit the wrench. And then down at the bottom, you have degrees and radians. Make sure radians is highlighted, and mine is, so we're good. So go back here. So this is going to be 0.4142. And that would be using Desmos or your graphing calculator to find definite integrals. All right, discontinuous integral functions. So even if a function is discontinuous at a point, you still might be able to find its integral. So where is this function discontinuous? Well, this is a rational function. And remember, in a rational function, your denominator can't be 0. So where does the denominator equal 0 in this function? Well, x cannot equal 2 in this function. So my function is discontinuous at 2. And since the denominator equaled 0, and with the numerator, it would cancel, that's going to be a whole. So since it's removable discontinuity, you can still find the area under the curve, because a hole is so small it basically doesn't exist. It's infinitesimally small. So you're still going to be able to find the area under the curve at that point, or between 0 and 3. So what we're going to have to do this is you're going to separate this into two separate integrals. So we're going to integrate from x squared minus 4 over x minus 2. We can separate this into, we're going to integrate from 0 to 2, x squared minus 4 over x minus 2, and then plus integrate from 2 to 3, x squared minus 4 over x minus 2. Let's see if that works. If not, then we're going to have to factor and cancel. I don't know how Desmos is going to handle that. Let's see what happens. Let's get rid of all these guys. So if I integrated, it'll let me know right away because the first one won't work. If I integrated from 0 to 2, and then I did x squared minus 4 divided by x minus 2, and then I did dx, that's going to be 6. So it does let me do it. So it's going to be 6 plus, and then I'm going to integrate from 2 to 3 of that same thing. So 2 to 3, and then x squared minus 4, and then divided by x minus 2, and then dx, and I get 4.5. And if I added those two pieces together, I'd get 10.5. I wonder if Desmos would let me go just start to finish of that, or if I had to separate it. So we want to go from 0 to 3. Let's see if it would let me do it. Oh, it does. So Desmos just lets you do it even if there is a break in the graph. So that's cool. All right. So on the next one, we could use Desmos to do it, or we can graph this. This was one of those functions when we were doing back in pre-calc. I said it was a common one that showed up. It's kind of weird looking, but if we made a table of values and evaluated this, let's try it. So if I plugged in 0, I would get undefined because the denominator can't equal 0. If I plug in 1, I get absolute value of 1 over 1, which is 1. If I plug in 2, I'd get the absolute value of 2 over 2, which is 1. If I plugged in 3, I'd get the absolute value of 3 over 3, which is 1. What if I plugged in negative 1? Well, I'd get the absolute value of negative 1, which is 1, over negative 1, which is negative 1. If I plugged in negative 2, I'd get the absolute value of negative 2 over negative 2, which is also negative 1. And if I plugged in negative 3, I'd get negative 1. So if I went to graph this, what it ends up looking like is I'm undefined at 0, and then I have the point 1, 1, 2, 1, 3, 1. So it doesn't exist at 0, but other than that, it's a horizontal line. And then underneath that, I've got negative 1, negative 1, negative 2, negative 1, negative 3, negative 1. So again, it doesn't exist at 0, but I've got another horizontal line at negative 1. And it wants me to find the area between the graph and the curve between negative 1 and positive 2. So that means that I'm finding the area of that rectangle and that rectangle. So if I do that, the area of this rectangle, since it's underneath the x-axis, it's going to be negative. The base is 1 and the height is 1, so the area of this little piece is negative 1. And then up above, this base is 2 and the height is 1, so the area of that piece of the integral is going to be positive 2, so this is going to be 2 plus negative 1. So the area of that function between negative 1 and 2 is going to be 1. Or we can hop over to Desmos and find that integral. So functions, miscellaneous, we're going to integrate from negative 1 to positive 2, and then we're going to do the absolute value of x, and then divided by x.